Hi everyone, in this video we're going to walk through a lab activity involving a titration of a strong acid, hydrochloric acid. And of course, like any titration, the thing that we're analyzing, which is called the analyte, has an unknown concentration. And you can see here, I've just marked this with a question mark for the concentration. We do not know the concentration of the hydrochloric acid. The hydrochloric acid is our analyte. We're going to titrate it with sodium hydroxide. The sodium hydroxide that's in this burette is the titrant. And the sodium hydroxide is 0.1 molar. We know the concentration of our titrant, and you can see this is the solution I'm using. It's 0.1 molar sodium hydroxide, a base. So I'm going to be titrating an acid with a base. Now the way we're going to do this is to take a small volume of the analyte, and I'll use a pipette and pipetter to do that. I'm going to take 6 milliliters of this acid of unknown concentration. I'm going to put it into this beaker, which I'm going to be using to titrate. All right, now that I've got some safety glasses on, we can get started. Now, like I said, I'm going to be using 6 mils of the analyte, and we're going to want to make a note of that because that's going to be critical to determining what the concentration of the analyte is. 6 milliliters of the analyte hydrochloric acid with unknown concentration. Let's take a look at the setup that we're using. I've just put 6 milliliters of the acid into this beaker, and you can see I'm ready to measure the pH of the solution. However, this is not the pH of the solution before titration begins. This is the pH of the buffer solution that is storing the pH electrode. So let me talk a little bit about this piece of equipment. The piece of equipment that I'm using here is a pH sensor, and the pH sensor gets stored in a solution that has a pH of about 4. Before I transfer that into what I'm titrating, I want to rinse it off to make sure that that solution that it's stored in is not affecting my result. Now you can see I've set it in there, and it's not quite far down enough to reach the solution. So what I'm going to do is add some water and make sure the water level gets brought up to where the pH sensor is actually submerged into the solution. And you may wonder why adding water does not invalidate our result. Well, we know that we added 6 milliliters of the analyte to begin with. Now that that volume has been recorded, we can add as much water as we want. The 6 milliliters we started with is the only number we're going to need in our calculations. So you can see right now the pH meter says it's reading a pH of about 6. That's not the solution's pH either. It's not even touching the solution of the 6 mils of acid. It's just hovering in midair. So I'm going to add 100 mils of distilled water, and it looks like that will be just enough to submerge the sensor. So now the sensor is actually measuring the pH of the solution. You'll notice the pH of the solution is pretty low. That makes sense. It's an acidic solution. Let me make sure it's submerged all the way, and then we can begin titration. All right, so you can see that the pH of the solution before titration begins is about 2.32. It fluctuates a little bit, but we'll make a note of the fact that it's beginning at a pH value of 2.32. Now that makes sense. We're titrating a strong acid, and right now we haven't added any base, so the pH is pretty low. In addition to measuring the pH as we titrate, we're also going to be adding some phenolphthalein. And remember, phenolphthalein is an acid-base indicator which will turn pink when the solution is basic. So I'm going to add just a little volume of phenolphthalein. The exact amount doesn't matter because it's just a qualitative indicator. Once the solution becomes basic, we'll see a pink color appear. So you remember the basic principle of titration is we're going to be adding the titrant to the analyte, adding base to acid, until we see the pH change to about 7. Now I'm going to be recording pH periodically here so we can make a graph of pH as a function of volume of base added. The first point that I want to record is this one where the volume of base added is 0. Now the LabQuest reads 2.32 before titration has begun. I'm going to tap Keep to record the first data point. And I've set it up as events with entry, which means every time I tap Keep, it's going to prompt me to type in the number of milliliters of base that I've added. And right now I've added none. So I'm going to type in 0, and I'm reading that from the burette. So notice I'm now going to add 1 mil. And you'll see a pink color appears here. However, it's going to disappear in a moment, especially since I'm going to be stirring the solution. It just takes a little while for those hydroxide ions that I just added to react with the excess hydronium that's in the solution. You can see that the pH increased by just a small amount. Now I want to record that second data point. I tap Keep, and the volume of base that I've added is now 1. Let's take a look at the graph that's being plotted. The pH has increased a little bit. I'm going to keep adding 1 milliliter at a time and see how the graph looks. So now I've added a total of 10 milliliters of base, and each time I've added 1 milliliter, I've recorded the pH. You can see that the pH is increasing, but it's not increasing in a linear fashion. I've added a few more mils, and notice every time I add 1 milliliter of base, you see a pink color appear for a moment, and it disappears. I tap Keep. I type in the total volume of base that I've added up until this point, which I'm reading from the burette. Tap OK, and I notice that now I'm getting to a point where the pH is increasing pretty rapidly. The pH is 4 now, and you can see the graph is starting to get very steep. I'm going to slow down and add a smaller amount of base each time, because I'm getting very close to the endpoint. Right now, the total volume of base that I've added is 14.5, and the pH is very, very close to being neutral. So I'm going to add just 1/10 of a mil. 1/10 of a mil will be enough to increase the pH significantly. I can do that by just turning this burette handle 180 degrees, and that essentially adds 1 drop. Adding just that small volume of base caused the pH to increase dramatically. It's all the way up at 6.52. That is as close to the endpoint as I think we're going to be able to get. The very next volume of base that I add will drive the pH up significantly from there. Just a half turn of the burette adds just an incremental amount of base, and you can see if I do that one more time, then we've already exceeded, I think, the endpoint of the titration. It takes just a moment for the pH to stabilize, and you can see that pink color is staying for at least 5 or 10 seconds, and that means we've reached the endpoint of our titration. I'm going to go and store that last data point. Tap Keep. Right now my burette reads 14.65. I can record to the nearest hundredth of a milliliter because it's right in between two lines. Notice that the pH at the endpoint of our titration, or as close to the endpoint where we're going to be able to get, is 7.16. At this point the solution is pink, but we're going to continue to titrate to get the second half of our graph. I'm going to add another half of a mil, bringing the total volume up to about 15, and I'm going to record that point. And I'm going to continue to add base at increments of a half a mil at a time and see what the rest of the pH curve looks like. So I continued to add base a half a mil and then 1 mil at a time, and you can see what happens to the titration curve. It's starting to level off. The solution is a bright dark pink now. It's very, very basic. So what's the result? What's the end point of our titration, and what's the concentration of the acid that we are trying to determine? Let's first discuss what the end point of the titration is and how many milliliters of base were required to neutralize. The end point of a strong acid, strong base titration is understood to be the point at which the pH is neutral, 7. We can find that point on our graph, but we remember that we recorded a pH of 7.15 when 14.65 milliliters of base had been added. So that's the number we're going to need to use in our MAVA equals MBVB calculation to determine the molarity of the acid. Remember, we know the volume of the acid that we used initially was 6 mils. The volume of base that was required to neutralize that was 14.65 mils. And of course we know the molarity of that base. The substance in our burette, called the titrant, was 0.1 molar sodium hydroxide. So you might argue that the volume of base needed to reach the endpoint is actually somewhere in between 14.60 and 14.65. Since we weren't able to reach a pH of exactly 7, we could estimate that. But remember, the last digit in a measurement is always considered to be an estimate, and it's still a significant figure. So the volume of base required to reach the endpoint in this lab is 14.65 mils. That corresponds to the place in the graph where the change in pH is most rapid. Right in the middle there, where pH increases very, very rapidly, is called the inflection point. And that's going to correspond to the end point of our titration. So I hope this introduction to acid-base titration was helpful, and this will give us a chance to understand this important procedure. Let me know if there are questions. We'll see you next time.